All right, so welcome to Thursday of week 8. So this should be lecture number 16. And we are now on chapter 18. That's my last class. We don't need that. So it should be right here. And okay, so 18, right? We have these things, these hypothesis tests, we have these confidence intervals. In both situations, the goal is to take your sample and infer information from the sample about the entire population. And there are conditions that must be satisfied before you're allowed to do that. Okay, so this box here in front of us lists the 3 conditions that must be satisfied before you're allowed to use the confidence interval and hypothesis testing formulas that we had on Crunchit, or that in general we had formulas for. The first one is it must come from an SRS. You can't have any problems like non-response or under coverage or obviously biasness or any of the issues that you might have in a real life situation. It has to come from an SRS with no problems. Okay, and we want the population to be large compared to the size of the sample. In this class, I have never seen on a test, not to say it's not possible, but I've never seen on a test a situation where they try to trick you and they give you a situation where you're not allowed to do any computation. Okay. But in real life, if you're ever actually going to work as a statistician or analyze someone else's work, then you have to make sure that the data comes from an SRS where the population is large compared to the sample size, and there is no practical difficulty. But the basic idea, the one that we normally check without really caring about the rest, is that it comes from an SRS. Condition 2 is that the variable we measure has an exactly normal distribution. It must come from a normal, not an approximately normal, but from a normal. Now, in real life, are things normal? Who knows? But usually what happens in real life is they say, not in real life, but what happens in tests or in homework questions or in quizzes, is they say, assume that we're dealing with a normal distribution. So that way you don't have to worry about it. Because again, if it's not normal, you can't do any math. And how boring would that be if you can't do any math, right? And question 3 is, in this example at least, we do not know mu, but we do know sigma. And as we go into further chapters, we're going to have situations where maybe we don't know sigma. Maybe it's not a normal population. And then the question becomes, well, what do we do in those scenarios? Are we shit out of luck, or do we have a fallback plan? Right now, we're only doing the basics of confidence intervals and the basics of hypothesis testing. And right now, these things must be satisfied, or else you just straight up can't do them. Does that make sense so far? I hope so. Let's see, someone said something. What did you say? It said, yes, okay. Well, you can't really argue with that one. Yes. Okay. Um, so I want clear. Okay. Um, so this is just repeating what we did. Where the data comes from matters. Essentially, what it's saying is, if you have an SRS, then don't worry about it, and everything is taken care of. And the rest of it's not really that important. A lot of filler stuff in these chapters. These books can be like 9 pages long, and you learn just as much. Okay. So now let's talk about cautions about confidence intervals. Okay, so remember that the margin of error, and before we talk about this caution. Someone remind me what's the margin of error again for the example that we did? Anyone remember the formula for the margin of error? The margin of error. Anyone recall what that formula was?
Wasn't it the z critical times the standard deviation divided by square root n?
Excellent, right? So the margin of error is given by this formula. Z star. This is not getting any better. Hold on. Z star sigma over the square root of n. The margin of error in a confidence interval covers only random sampling errors. It does not cover errors that come from other real life situations like undercoverage or non-response. It does not take those into account. What do you think would happen to a margin of error if we did take those into account? Would the margin of error get bigger or smaller? It would get bigger, exactly, right? The margin of error is this is the part that I don't really know, right? Well, if you have other things to worry about, then the part that you don't really know is going to get bigger. Okay, in this class, again, I have never seen a problem where we had these and you had to mathematically take them into account. It just gets too mathematically complicated. Okay, so let's do a question number 4 there. What's your weight? A 2015 Gallup poll asked a national random sample of 398 adult women to state their current weights. The mean weight in the sample was X bar equals 155. So here we have 398. That's an important number. It's going to play a role in formulas. We have X bar equals 155, an important number, plays a role in formulas. We will treat these data as an SRS from a normally distributed population with sigma equal 35. In that one sentence, it essentially covered all 3 of the requirements to be allowed to use our formula. SRS, normally distributed, and we do not know sigma. We do know sigma, we just don't know the mean. So A, give a 95% confidence interval for the mean weight. So first, what's the formula in general, the generic formula for confidence intervals? What's the generic formula for confidence intervals?
X plus or minus, or X bar plus or minus margin of error.
Excellent. X bar plus or minus the margin of error. In our example, X bar was what?
$155.
155. Plus or minus. We'll skip Z star for a second because the other parts are easier. What's sigma?
35.
35. They gave me that. What's N?
398.
398. So the only question that becomes is what is Z star? How do I find Z star? How do I find Z star?
Don't you look at the C table?
You could. Of course, at this point, it should be immediate because we had a list of this is Z star in this case, this is Z star in this case, this is Z star in this case. What in the problem tells us that what case we're dealing with? And then what is a Z star for that case?
Would it be for
It's a
95?
95%.
95% confidence. And 95% confidence automatically comes with a Z star. What is it?
1.960.
1.960. So that is my confidence interval, 155 plus or minus the margin of error. Of course, normally we like to do a confidence interval as an interval. So we want the left edge of the interval and the right edge of the interval. How do I find the left edge of the interval?
You minus it.
Oh, someone plugged into Crunch It. So minus 1.96 times 35 divided by the square root of 398 and got 151 point whatever. 151.3. And then if I do the same problem, but this time I change a minus sign to a plus sign, I get 154.8. And is that what he said? Yeah, pretty sure I did it correctly. Yes, you did. Okay. Oh, don't go there. That wasn't the point. How do I move this? There we go. Okay. Now, B. Do you trust the interval you computed in part A as a true 95% confidence interval for the mean weight of all adult women? Right? I didn't get 154. No, I got 154.8. Oh, wait. I hit a wrong button. Ignore both of my answers. I hit a wrong button. Sorry. I hit minus instead of times. That was my bad. No, that was me. So eraser, I get 151.6. And then that's for the minus. And for the plus, I got 158.4. That was on me. I scared you. Well, it's near Halloween, so it's the season for scaring, isn't it? That was the whole plan. B, do you give us gave us a see? I'm a scary guy. What can I say? B, do you trust the interval you computed in part A as a true 95% confidence interval for the mean weight of all U.S. adult women? Why or why not? Do you trust it? Anyone? Bueller?
Do we have to calculate P now?
Don't got to calculate anything. This is a psychology question. No. That's not the reason. That's not the reason. It's not a statistics thing. This is a psychology thing. Do you trust your confidence interval? Are you truly 95% confident that the true value of the mean weight of adult women is between 151.6 and 158.4? I trust it. It seems pretty chill. You're all missing the points. Come on, could someone chime in here on why I may not trust? What the freak? Can you guys see what this bar, or is it only in my end? Whatever. Can you guys come up with a reason why you should not trust it? $398 is a lot of people. That's a pretty big sample. It's a Gallup poll, someone says. So what? Gallup polls are very reliable polls. No, because most Americans are overweight. No, listen, this poll was taken, right? It was a survey.
Is it no because some people lie about their weight or they round their weight?
There you go, right? It's no because most people are not very honest when it comes to reporting their weight. That's a psychology question. It's a psychology question, not a statistics question. But it just shows you that just because a poll or a survey or something says something, that you should automatically say, oh, that's it. I mean, just go back 4 years. Not to say I'm not on one side or the other in this discussion. I'm just saying that I believe before the election results or election day last year, pretty much every poll showed Clinton in the lead, and yet Trump won, or at least won the electoral vote. So it just goes to show that people are not always honest in their answers. I was about to make a joke about that earlier, but alas, it's not a joke. It's very, very serious. All right, does that make sense? Questions on that one? Let's just do another one just for fun. Electoral college, yeah. Right? He won the electoral college, right? I'm not really into politics, but I'm pretty sure he lost a popular vote but won the electoral college, right? Well, whether it's fair or not, that's not for me to say. I'm not a political science major. I don't know anything about that. I know people on both sides who are very adamant that it's either a great thing or a horrible thing. I don't know enough about it, and therefore, as an intelligent person, or I like to believe that I'm an intelligent person, I choose not to discuss things for which I'm not an expert in. I listen to people's opinions, and I say that sounds good or doesn't seem reasonable, but I don't then convey my own opinion, because my opinion is based upon nothing, essentially. What do I know? I know math, I know physics, I know chemistry, I know chess, I know that's basically it in my life. At the end of the day, it's pretty much nothing. Okay, anyways, let's do question number 7. Do you drink pop? Now, I'm from the Midwest. When I was growing up, we called it pop, but here on the West Coast, they call it soda. I think the East Coast as well, soda. And even I really felt that I had converted from a Midwesterner to a Los Angelian the day that I unconsciously called it soda instead of pop. And I was like, oh, I'm finally here. Thank you very much. It was a wonderful day in my life. All right. So a July 2015 Gallup poll. I'm on a diet too, Leah. I'm on a diet too. Actually, I'm not, but I'll start eventually. A July 2015 Gallup poll asked a national sample of 1,009 adults aged 18 and over if they actively avoided drinking soda or pop, which is weird because soda and pop are really the same thing. So I don't know what they mean by soda or pop, but who cares? Let's move on. Of those samples, so let's underline important stuff as we read it. I don't care the year. It starts on Sunday. For me, mine starts in 10 days. Next Sunday. My birthday's the 24th. Can't start on my birthday. I already know what I'm eating that day. So it'll start on the day after. Okay. Maybe I'll go to Fogo de Chao the day before, and then I'll have my Korean barbecue, my Korean stuff the day of, and then Sunday. Jamar, yours the 24th as well? Damn, dude. Look at that.
Yeah, I'm a Scorpio.
Do you mind zooming? Scorpio, we're on the cusp, baby. Do you mind zooming in a bit on your screen, please? What does that mean? Me personally or the page? You can see the page, right? You can't see it? I don't know how to zoom. It's in my page, it's the entire screen. Do you not see that? Is that better? I hope it is. Okay, so let's read the question. It says, a July 2015 Gallup poll asked a national sample of 1,009 adults. Okay, 1,009, that seems important. That's my sample size. 1,009 adults, age 18 and over, if they actively avoided drinking soda or pop. Of those sampled, 61% indicated that they do so. That's the sample value. Gallup announced the poll's margin of error for a 95% confidence as plus or minus 4 percentage points. So when they say it's 61, what they really mean, it's somewhere between 57 to 65. Right? Somewhere, I might need glasses then, that's possible. I got LASIK done almost 20 years ago. And my eyesight is still so amazing. I can hold up any number of fingers in front of my face and tell you how many fingers without a problem. I'm an expert. 2, 4, 2, 3. I can do it all day long. Anyways, so we have the Gallup poll, 57-65%. A, Gallup dialed land. I know it's amazing. I'm an amazing person. What can I say? Gallup dialed landline telephone numbers at random, and so missed all people without landline phones, including people whose only phone is a cell phone. That's part A. B, some people whose numbers were chosen never answered the phone in several calls, or answered but refused to participate in the poll. And C, there is a chance variation in the random selection of telephone numbers. Which of the following sources of error are included in the margin of error? A, B, or C? Which are included in the margin of error? B, 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 B. Is it Doug Gardner? Sorry, I'm getting work done at my house. He might be here. Dad? He's here. If you want to go downstairs? Okay. So everyone said B, it looks like. Now, I don't know if everyone actually said B because they believe that, or they're just following along like a lemming. My he's going down. He's going down. And then we have an A. I think the answer is actually C. Boom! Oh, I'm so good. I should teach this course. Oh, wait, I do. So why is the answer C? So rigged. Because remember, the margin of error comes from the math. The math takes into account that there's always going to be variation. When I typed B, I really meant C. Of course. Oh, bullshit. Sorry, something in my throat. So the margin of error comes from the math. The math is all about chance variation. You know, you're going to get different values. They're all over the place. A and B are practical problems. People who don't have lines, that's what we call undercoverage. You can't get everyone. People who don't participate, that's non-response. Those are practical problems. They don't pop up in the math. They pop up in the, you should really extend this margin of error, because if you don't extend the margin of error, it's not going to quite be as high as it's supposed to be. So that is that one. Okay. See, I'll tell you, man, everyone said A and B. Sorry, everyone said B, but one person said A. And I'm like, no, I'm going with C. So yeah, confidence. That's what I'm talking about. Anywho, let's go on to the next section, which is cautions about significance tests. Significance tests are used widely in most areas of statistical work. They're all over the place. You might not see them like, hey, there's a hypothesis test, but they are all over the place. Okay, so what are some of the things that we need to be worried about? First, what do people say here? Yes, everyone gets lucky every now and again. That must be what it is. I can't think of any other. Okay. Whatever. Okay. So first, the first question is, how small of a p-value is convincing evidence? Okay. We know that the smaller the p-value, the more likely it is that the null hypothesis is incorrect, that the result is statistically significant, and that we want to reject the null hypothesis. The question is, how small do we need to be convincing? Okay. So there's two things you should ask yourself. First, how plausible is the null hypothesis? Okay. If the null hypothesis represents an assumption that the people you must convince have believed for years, then you're going to need very strong evidence to persuade them. What's an example? So, what is the average temperature, or what is the temperature of a healthy person, of a healthy adult? What is anyone know the temperature of a healthy adult? Growing up, have you ever heard what
98.
what is it?
6.
98.6. Okay. Growing up, there was always 98.6, 98.6. Suppose you don't really, yeah, it is normal to have a range of values, but for years, 98.6 was chosen as the benchmark for of a healthy temperature. I remember once I got my temperature taken for something, and while the person was taking it, I said, it's like 99.8 or something. I mean, I just randomly picked a number, and he's looked at it, and I was right. I was right on the money. And he goes, "How do you do that?" And I said, "Oh, I can regulate my internal bodily temperature." And of course, you say it with a straight face because you got to be impressive and whatnot. And he thought I was serious, so he wasn't really smart. But anyways, the point is that the point is that 98.6 is a cherished belief amongst everyone of what the average temperature is. Now, let's say you do not think it's 98.6. I know it's amazing, right? I'm an amazing person. What if you don't think it's 98.6 and you say, you know what, I believe it's different? So you do an hypothesis test. You do H naught, mu is equal to 98.6, and H1 or H8 is mu is not equal to 98.6. It's something else. Maybe it's bigger, maybe it's smaller, whatever the case may be. In that case, you're going to need, yes, that would have been funny, but I didn't do it. In that case, you're going to need very strong evidence to convince people, because people have a hard time letting go of their beliefs. You see it all over the place. In particular, again, it's a subject that people are very passionate about, which is politics. Especially, it's October, right? We have this election coming up. It's on everyone's mind, except for mine. I just don't care. But most people are very strongly on one side or the other, which is fine. You have your opinions and you have your beliefs. But at the same time, in my experience at least, most people are unwilling to listen to the other side, or to say those magic words, "Oh, I never thought of that," or "You make an interesting point," or "That's interesting."
Okay, so you just want to redo, you just want to one.
I want to, yeah, I want to
just redo it.
Basically, yeah.
Okay, 2,500.
Seriously?
Yeah. Too much? You can try to reseed it.
Reseeding will probably be cheaper, right?
Probably.
Because I paid like $5,000 for the whole thing in the first place. It shouldn't be that much to do the whole thing again. I mean, the cement and everything was $5,000.
Oh, really?
Yeah. Anyways, I'm teaching right now, so I can't do this right now.
Okay.
But if you can get it down cheaper, go for it.
Yeah.
Okay.
Yeah.
All right. Sorry about that, guys. But if we have to, that's fine. That's not a lot of money, so that's okay. Okay. Anyways, so in that case, when the beliefs that people have is really tough to uproot, you're going to need a very small cutoff, and 5% might not cut it. You might need 1% cutoff. In physics, for example, when they look for elementary particles and particle accelerator experiments, you can't actually see a proton or an electron, I mean, you can now to some extent, but you can't see these particles. But what you can do is you can examine the effects. You can say, well, if the particle was there and it had these properties, then this is what should happen. And if that thing happens, then we have evidence that the particle was there in the first place, even though we couldn't see it. Multiply this by 1,000 to a scale that most people can't really comprehend, and you have the idea of what particle physicists do. They look for consequences of their beliefs, macroscopic consequences of their belief for microscopic theories. And they need very strong evidence. I think for physics, it's got to be less than a 1 in a million chance of being wrong. I think their p-values have to be like 0.00001 or something like that. Very small for there to be what's called statistical evidence. Okay. So, anyways, first question is how small of a p-value do you need? The other question is, what are the consequences of rejecting the null hypothesis? Sometimes, if you reject the null hypothesis in favor of something else, you might have to recalibrate equipment, retrain your staff, hire more people, do this, do that. The consequences of being wrong can be so significant that we again want to make sure that we don't make an error. Okay. We again want to make sure you don't make an error. In that situation, again, you might have a smaller p-value to take into account the risk, the worry about what happens if you're wrong. Okay. So even though in general we do 5%, just remember there's no universal rule of 5%. It's just guidelines. And if they don't give you one, just assume it's 5%. But it's not always 5%. Does that make sense? Yes, no, I hope so. I hope so. Let's read this box here. Sample size affecting statistical significance. The larger the sample, the small variation, because we know by the law of large numbers that you kind of near in on the true value. Okay, so because large random samples have small chance variation, very small population effects can be highly significant if the sample is large. If the sample is too large in comparison to the population is very small, we have issues. This is why the samples cannot be too big compared to the population. Okay. Essentially what it means is as follows. As a practical application for this class, you're never going to really have to worry about the population being too small in comparison to the sample. Okay. If the sample is too big or too small, we run into other issues. Okay. If the sample is too small, then we don't have enough to really stabilize around a particular value. So if the sample is too small, that's not good. Okay. If the sample is too large, then if you have something in regards to the entire population that might skew your results, what happens is it manifests itself too greatly in the sample, so that we don't want the sample to be too large either. There's a sweet spot, and I think it's like the sample should not be more than 100th the size of the population or something like that. I think it's in the book somewhere. I'll look for it. I don't know the exact number because it's just a guideline anyways. Okay. But when it comes to statistical significance, this just tells us whether or not the result is unlikely given the assumption of the null hypothesis. It says nothing about practical significance. Sometimes you might say, yeah, I'm going to reject the null hypothesis, but I'm not going to do anything because who cares? Okay, so the null hypothesis is wrong. I'll live with it. You have statistical significance, but you don't have practical significance. Okay. And I'm not even sure if there's a nice example of that here. Let's see, they have an example of the difference between statistical and practical. No, they don't even talk. They just mention it. They don't even really do anything with it. Hey, Professor. Oh, welcome. Did she get in okay? Is she here with you now? Are you on the phone driving back? Sweet. Tell her I say hi. Okay. So now we will do a little bit more math, right? Hopefully you didn't think math was over. So she's with her at home now. Well, tell her that we wish that she would have joined us for class, but I guess she's unpacking or whatever. Okay, so planning studies. Sample size for confidence intervals. Someone remind me again. I'm not sure why I took out a pen. I'm just going to do it here anyways. Someone remind me again, what is the formula for the confidence intervals? We only have one formula so far, so what is it?
X bar plus minus Z star sigma over square root of n.
X bar plus or minus Z star sigma over the square root of n. Okay, so to get a confidence interval, you need the sample mean, the population standard deviation, the confidence level, which ultimately gives you your Z star, and the sample size. And the margin of error is going to be that value. The margin of error is going to be Z star sigma over the square root of n. Now let's say going into the experiments, but before you take the experiment, before you actually do the experiment, let's say you say to yourself, you say, you know what? I want to really rely upon my answer that I get. And for me to really rely upon the answer that I get, my margin of error can't be too big. So I want to limit my margin of error to 0.1 or 0.2 or 17 or some number. You want to make sure that your sample size is large enough that the margin of error is a given size. Because if you look at your sample size, it's in the denominator. So we know that what happens as the denominator goes up, the margin of error gets smaller, correct? Because as the denominator gets larger, the fraction of the whole gets smaller. The question is, if in advance I decide that I want to have a specific margin of error, how do I determine the sample size needed for that margin of error? Well, mathematically, it's not very complicated. We just solve for n. The first thing we're going to do is take the margin of error and divide by Z star. So you get m over Z star equals sigma over the square root of n. Correct? Yes? And then we're going to square both sides. I mean, there's more than one way to solve for this. I'm just doing it one way. We square both sides. So I get m over Z star squared equals sigma squared over the square root of n squared, which is n. And therefore, what is n equal to? If I mathematically solve this for n, what do I get?
Sigma squared over m over z squared.
Yeah, another way of writing it mathematically, which you can check is mathematically the same, is just take sigma Z star over m and square it. M stands for margin of error. So if you say, I want my margin of error to be 0.1, and then you say, okay, what should my sample size be to ensure that I get a margin of error that's no bigger than 0.1? This is the formula. Now, when, question?
That's so much energy.
No. So when you plug this into your formula, chances are you're not going to get a whole number. All right, we're solving for n. We're solving for the sample size necessary to ensure that we have a, sorry?
Just, like body mods.
You know, I just
Body mods.
That was interesting. What the hell's a body mod? I don't know.
I think Hannon's mic is on.
Yeah, someone's mic is on. It ain't mine. I mean, it's also mine. But anyway, so if you plug in these numbers and you solve for n, let's say you get something like 3,117.2. Well, you can't ask 3,117.2 people. That does not make any sense. So what do? Do we go down to 3,117 because it's closer? Or do we go up to 3,118 because it's further? What do we do in a situation where the math does not give you a whole number?
Just go up. There's nothing wrong with adding one more.
Well, yes, you always go up. You always go to the next number up. Because remember, we're looking for the minimum number necessary to ensure that your margin of error is small enough. If you ask more people, no problem. Hey, ask the more the merrier. But if you ask fewer people, that's not good. So you always go up. You never go down when it comes to margin of error. Okay, not to account for the error so much. You go up, and not to account for the error. You go up because going up makes a smaller margin of error, and going down makes a bigger margin of error. And your goal is always to make a smaller margin of error if possible, right? You never want a bigger one if you can get a smaller one. So let's do an example of this, just straight up plugging things in. So here we have a question, example 18.5. It says a psychologist recorded the size of a tip of 20 patrons in a restaurant when a message indicating that the next day's weather will be good was written on their bill. The population standard deviation is 2, sigma equals 2. And we want to estimate the mean percentage tip mu for patrons of this restaurant who receive this message on their bill within plus or minus 0.5 with 90% confidence. Now we asked 20. Is that enough to get a margin of error within plus or minus 0.5? Well, let's take a look. The sample size needed, n, is equal to this formula right here. The margin of error goes in the bottom. So the margin of error is 0.5. And sigma is on top. Sigma is 2. And we need Z star. What's Z star for a 90% confidence interval?
1.645.
1.645. So when I take out my calculator and I do 1.645 times 2 divided by 0.5, and I square that, the math gives me 43.2964. What the hell? Okay, 43.2964. So what do I do with 43.2964? What's my final answer?
44.
So I round up, and the answer is 44. How many did they do in the problem? Let's take a look. They did 20, right? But what do they say? 43.3, but always round up to the next higher whole number when finding n.
I have a question.
I have an answer.
Does the negative or positive of the margin error not matter? How
No.
you write it in the question, or is it
No.
always positive?
The margin of error is a positive number.
Okay.
The margin of error is always a positive number. And 1.645, yeah, okay, good. So you can reverse engineer the sample size you need to ensure that your margin of error is no bigger than a certain amount by this formula. Make sense? It's not too bad, I
Yes.
hope. Okay.
Professor, I had a quick question about what you said about whether it's if you increase the number or decrease the number,
Okay.
the margin of error would change. So let's say, like if you decrease the amount in your sample, was that what you were saying? Or
If you decrease the amount in your sample, the margin of error goes up. Smaller sample size means a bigger margin of error, correct?
Yes.
because if the denominator, right, if n gets smaller, if my denominator gets smaller, the fraction as a whole gets larger, right? So n goes down, margin of error goes up.
Mhm.
Okay, but I want a smaller margin of error, not a bigger margin of error, not a bigger margin of error. So to get a smaller margin of error, I can make n larger. Right, exactly. If I know that 43.3 is the exact cutoff, but that's a mathematical impossibility to ask 43.3 people. Anything less than 43.3 won't get me what I want. Anything more than 43.3 will get me what I want. So what's the smallest number that will get me what I want? 44. Sample sizes always go up, never down. Does that make sense?
Yeah.
That makes sense.
Okay.
Yes.
So then we have the last section of chapter 18, which is the power of a test. Power of a test. So to do this, I'm going to introduce a few terms, which I don't think the book introduces till late. Oh, here they are. Okay, good. So I'm going to introduce a couple terms, and I'm going to make a nice little chart. Now, if you come to, if it magically ends up with a whole number, then that's your number. Okay, if you have a magical coincidence margin of error z star sigma for a whole number, then that's your number. The problem is this. Even though we use 1.645 and 1.96 and all those numbers as approximations, they're never exact, which means you should never end with a whole number if you take enough decimals. Okay? Okay, so let's make a little chart here. I need a little room. How do I, okay, I guess I'll try to fit it in. So here we're gonna have the following. Yes.
I think on your left corner where the little arrow is, where it says chapter 18, you can close that. I don't know if you'll be, maybe that'll give you more space to write. No, never mind.
No, it looks like it's just
Okay,
maybe, huh?
never mind. Sorry, it's because on
No,
mine it gives you more
it works.
space.
It works.
Oh,
It
there
works.
you go.
You're a genius. Oh, I don't mean to. You're a genius. Okay. So here's what we're gonna have right now. I'm gonna make a little chart here. I'm gonna make a little chart. So that's right. If you get, just to go back, someone asked a question. If you get 20.01, you round to 21. That's correct. You always round up. So you have two possibilities, right? Either the null hypothesis is true or the null hypothesis is false, right? It's got to be one or the other, right? Yes? No? Maybe so? It's got to be one or the other. And you can do two things. You can either reject the null hypothesis, or you can not reject the null hypothesis. Right? So there's two possibilities for the null hypothesis. Either it's true or false. And you can do one of two things, either reject it or not reject it. So overall, there's 4 scenarios. Are any of those scenarios, I guess for lack of a better word, good? Did you do the right thing in any of those 4 scenarios? Did you do the right thing in any of those 4 scenarios? Think about it. But not too much. Which scenario did you do the right thing in?
When H naught is false and you reject it?
Yes, if H naught is false, you certainly want to reject it, correct? So this square is a happy square. You did the right thing. Is there any other square where you did the right thing?
Bottom left.
The bottom left. If H naught is true, if H naught is true, then you do not want to reject it. In that scenario, you again have done a good thing. Apparently I'm a Picasso. I didn't even realize it. If I was a Picasso, like my other eye would be like here or something like that. But anyways, now, if the null hypothesis is true and you reject it, did you make a good decision? Did you make a good call? Did you do something that was right or wrong? No, you made an error. We call this one a type 1. Oh, crap. Type 1. Well, I can frown, it's true, but I don't want to frown. Frown is bad. Because there's a difference between a type 1 error in this box and a different type of error in the other box. So this one we're going to call a type 1 error. No, you don't get mad. You don't get mad, but you get sad, so it's like, there's a little tear. I look like I don't even know what I look like, but that's horrible. What?
Oh, are you on?
I'm on, yeah, I'm teaching. What do you want?
Bye.
Go now. Unless you want to bring me food, in that case, that's always okay. Just go. So then, I know I was also going to say it was a cat. Michelangelo. What does that say? Michelangelo over here. Okay, so now I was Picasso, but now apparently I'm Michelangelo. So I guess Picasso doesn't draw cats. That must be what it is. So anyways, okay. Now, what if H naught is false and I do not reject it? Did I make a good call there? Da Vinci. Good old Leonardo. So is this a good call or is this a bad call? If the null hypothesis, it's a bad call. We call this, can anyone guess? I'll give you one guess. We call this a type 2 error. Usually they use Roman numerals, but it really makes no difference. So type 1 error, I'll use Roman numerals. Type 1 error. And then we have a type 2 error. So alpha, which is also called the level of significance, which we've used before, that's our cutoff point. Alpha, the level of significance, is equal to the probability of making a type 1 error. How likely is it that you make a type 1 error? That is alpha. Beta is equal to the probability of making what? A type 2 error. Beta is equal to the probability of making a type 2 error. the power of a test is just 1 minus beta. Now, let's think about these three a little deeper. If you make a type 1 error, that means a null hypothesis must be true, right? You rejected it when it was true. If null hypothesis is true, then mu has a very specific value. But for beta, it's the probability of making a type 2 error. If you make a type 2 error, the null hypothesis is false. How many ways can the null hypothesis be false? Infinitely many ways. If mu is not 0, but rather greater than 0, there's infinitely many values it can be. So in reality, we have infinitely many possible betas, and therefore infinitely many possible powers. One for each of the alternatives. So when you're given a specific question, it'll always be, if this is the value, what's beta and what's the power? If this is the value, what's beta and what's the power? It will always say to compute beta or the power for a specific value of mu not being 0, or whatever the case may be. Let's do an example. Let's find an example here. Finding power, use software. So where's thanks. Precious. Okay. Dinner. Okay, so let's find an example that works. There's got to be a good example here somewhere. Oh, let's try this one as well. Okay, it says some software packages, for example, SAS, JMP, Minitab R, will calculate power. I'm not even sure if, I guess Cruncher can probably do it. We'll see, I guess, in a minute, if Cruncher can calculate the power of a test. But let's take a look. We asked Minitab, which is another program, to find the number of observations needed for the one-sided z-test to have power 0.9 against specific alternatives at the 5% significance level. In other words, actually, you know what? Never mind this question. This one is more complicated than I was expecting. Hold on. Ignore that. Ignore that. I apologize. Take that back. Just ignore everything I just said. Well, here, let's just do some skills. Okay, that's what we're going to do. Let's do some skills. Okay, let's do number 14. So let's go ahead and read it. So I underlined what I felt were the important things. Actually, there's more. It's also normal. So they gave me that it's normal, which is a very important thing to have. They gave me sigma. They say that in 2013, the mean score was 220. And I plan to give a test to a random sample, SRS, of 25 fourth graders to test whether the mean score for all fourth graders is still above the basic level. See, they were 220. My students are amazing. Are they still above 210? Well, if my null hypothesis is that it's 210, my alternative is that mu is greater than 210. Now, if the true score is really 220, then the null hypothesis is wrong. You learn that the power of your test at the 5% significance level against the alternative mu equals 220 is 0.346. Explain in simple language what 0.346 actually means. This is a one-sided test, that's correct. So power is 0.346. That's 1 minus beta. So therefore, if the power is 0.346, the power is 0.346, what's my beta? In this example, what's my beta?
0.654.
Okay. Now, beta is the probability of making a type 2 error. In other words, of not rejecting the null hypothesis when the null hypothesis is false. So if the null hypothesis is false, then mu is not 210. Well, what is it then in this example if it's not 210?
220.
220, right? We're testing specifically against this alternative. In other words, if the average reading score is really 220, then the likelihood of not rejecting the null hypothesis is 65.4%. The likelihood of claiming that the average is really 210, when in reality it's 220, would be 65.4%. And therefore, the likelihood of rejecting the null hypothesis, if it's really 220, is 34.6%. If it's really 220, we want to reject the null hypothesis. Well, there's only a 34.6% chance that that's going to happen. That's what the power of the test means. Explain why the test you plan will not adequately protect you against deciding that average reading scores in your district are not above basic level, because there's only a 34.6% chance. That's not very large. Let's do another one. Probably a little unclear, just having learned it. So let's try another one.
Could another reason be that the sample size is not big enough to be accurate enough to determine anything?
Well, the larger the sample size, obviously the more convincing your evidence, right? But whatever sample size you get, the numbers are what the numbers are without caring where they came from. So if my numbers give me a result, I don't say, well, the small sample gave me these numbers, but these are my numbers. Does that make sense? A little bit what I'm saying? Someone asked a question. He said, beta is the probability to reject the null hypothesis. Beta is the likelihood or the probability of making a type 2 error. That means not rejecting the null hypothesis when you should. Power is rejecting the null hypothesis when you should. Okay, high power is a good thing. You want to reject the null hypothesis if it's wrong. Okay, a high power does that. A high beta is bad because a high beta means that there's a high likelihood of making an error. You want to have low beta and you want to have low alpha. You don't want to make a type 1 error. You don't want to make a type 2 error. How do you get them both low? Because in general, the bigger one is, the smaller the other is. There's only one way to make both alpha and beta low, and that's by doing what? And what do you think is the one thing I can do prior to actually taking a sample to make alpha and beta both low?
Add more data.
Add more data. The larger your sample size is, the smaller alpha and beta are going to be. If you want them both to be small, just have more data. So let's look at 17. It says, use the statistical power applet, which I don't know how to find it. Actually, it's 1814. Is it this? I don't know, we'll see. Use the statistical power applet to find the power of the test. How do I do this? Oh, I can't. Okay, never mind. I can't do that one. See, most questions on power in this cluster can be very qualitative because the math is too hard. Yeah, so let's not worry about that. Let's see what else we have. Is that it? All right, let's do 25 and 26. Let's do 25. So let's read it. And the question is it A, B, or C? Okay, got a couple C's. Not sure, always good. Got a B. So, a medical experiment compared zinc supplements with a placebo for reducing the duration of colds. Mu is the mean decrease in days in the duration of a cold. A decrease to mu equals 1 is a practically important decrease, not significantly, but practically. You get better 1 day earlier. You get back to work, to productivity, to school, whatever the case may be. The significance level of a test, remember, alpha is the significance level. Alpha is also the probability of making a type 1 error. A type 1 error means rejecting the null hypothesis when the null hypothesis is true. So this is the probability of rejecting the null hypothesis, of saying probability of concluding mu is greater than 0, which is what our alternative is, when the null hypothesis is true, when mu is actually equal to 0. A, the probability that the test rejects the null hypothesis when mu equals to 0 is actually true. So I'm going to say A. Oh my God, it's A, crazy. Does that make sense? Notice how I don't do all the steps in my head. I write them out. The significance level of a test is alpha. Alpha is the probability of making a type 1 error. What does a type 1 error mean? Rejecting the null hypothesis, in this case, concluding mu is greater than 0, when the null hypothesis is actually true, when mu is really equal to 0. Well, that's exactly what A says. The probability that the test rejects the null hypothesis when the null hypothesis is true. Habit number 26 is a follow-up. A, B, or C for 26. I got a C, I got a B, I got a C. Keep going. Let's see some IDKs. Maybe a IDHAFC. Maybe a WTFC. Lots of possibilities. So the power of a test against the specific alternative mu equals 1. Well, let's go back to definitions. The power is 1 minus beta. Beta is the probability of a type 2 error, which is, I hate this, which is the probability of not rejecting H naught, of concluding H, the mu is actually equal to 0 when null hypothesis is false, when mu is greater than 0. Oh, I haven't gone that far. Bye, Carolee. Have a good time. So the probability of concluding that mu is equal to 0 when in reality mu is greater than 0. So if that's what beta is, then the power being 1 minus beta is the probability of not concluding mu is 0 when mu is greater than 0. That means of concluding that mu is greater than 0 when mu is greater than 0. Well, in our case, it's for a specific mu. Concluding mu is equal to 1 when mu is greater than 0. So the probability that the test fails to reject the null hypothesis. Let me fix this. My handwriting is a little off, affecting the reading. The power is concluding that mu is equal to 1 when mu is greater than 0. So the probability that the test rejects the null hypothesis when mu equals 0 is true, no. The probability that the test rejects the null hypothesis when mu equals 1 is true, good. Or fails to reject the null hypothesis. No, beta is when you fail to reject the null hypothesis. The power is when you do the right thing. The probability that the test rejects the null hypothesis when mu is true. So the answer is B. Remember, power is a good thing. If you fail to reject it when mu is 1, you just made a mistake. That's not power, that's bad. That's the opposite of power. So the answer is B. Does that make sense? We'll go over this next time because the test is coming up. But for now, officially, midterm 2, chapters 8, 15, 16, 17, 18. 5 chapters. When? I already said when. Probably, almost definitely, the following Tuesday. Not this Tuesday, but the following Tuesday. Which chapter? I just said which chapters. OMG. Way up. I go through life in a state of perpetual hunger, alleviated every now and again by being less hungry for short time intervals before I'm hungry again. 8, 15, 16, 17, 18, 5 chapters. Always hungry. That's right. Never say those 3 horrible words. I am full. Just erase them from your vocabulary. And then get sick like I am right now. My hands are all swollen. Like it started happening like the last 3 or 4 days. I don't know what it is. I don't know if it's like a diabetes thing because I was diagnosed a couple years ago and I did nothing about it. So I have no idea, but food's too good. I'll just eat till I die. What can you do? Just keep eating, right? That's the thing. Like drugs, you don't need drugs. So if you have a drug addiction, you can just stop doing drugs because you don't need drugs. But you need to eat. So just eat it. I don't know. So, if there's no more specific questions for today, I'll stop it, Ryan. Yeah, then stop it. So, I'll see you all Tuesday. Yeah, healthy stuff. That's the tough part.
Professor, before we leave, can
Yeah.
you unlock the homework for
Sure.
thank you.
I'll do that right now. Oh, no. All right. What's today's date? 15th?
Today's the 15th.
Yes.
All right. So I'll give you to the 20 I'll give you to the 31st. 11:59 p.m. on the 31st.
Thank you, Professor.
You're welcome. That'll be for the homeworks and it'll be for the practice quizzes. So now you don't have to bother me anymore by sending me emails. I'll do it right now. You know.
Sorry, one last thing. Were you ever able to figure out if you can reset the quizzes for the people that already took them, or was that just?
I have not. I still have to look into
Okay.
that. I still have to look into that. Send me an email to remind me. Otherwise,
I'll do that. Thank you.
You're welcome. All right, everyone. Peace in the streets, Professor. Peace in the streets. I don't know what that symbol that means, but rude. Oh, who's rude? What? I make no promises. Thank you. Oh, you heard that, huh? That was not intentional. Okay. For the quiz will be 16 and 17. Confidence intervals and hypothesis testing. You're welcome. All right. I need a break. I gotta do this homework. I forget otherwise. You're welcome. I'm just gonna hang up now.